Is the presentation visible?
Yes, madam.
Okay. Okay, then let's start today's discussion. So, welcome to the tutorial session of EMI, EMC, and signal integrity, week 3. Last week, we discussed about the computational techniques, how to compute uh, the Fourier spectrum coefficients in a more convenient way, and we solved the numericals based on that computational technique. And we saw we computed the Fourier coefficients of a trapezoidal waveform, uh, a square wave pulse, and different other waveforms. So today's topic of discussion is spectral bounds of trapezoidal clock, effect of rise time and fall time on spectral bound of a clock, and effect of ringing on spectral bound, and spectral bounds of linear systems. Now, first of all, what is spectral bound? So, so what we are seeing here, we are trying to find out that what will be the magnitude spectrum of a particular waveform, right? Suppose we have a waveform and what are the magnitude spectrum, right? And based on that, we will decide like what are the improvements we need to do so that our emissions will be lowered and it will not affect the performance of the nearby systems, all these things. So magnitude spectrum is really important. Okay. Now, suppose we have the frequency f or omega you can take, right? And we have a spectrum like this, and it gradually decreases as the frequency increases, the spectrum gradually decreases. Okay. Then we can take the envelope, right? We can take the envelope and we can say that the envelope is like this. Okay. So it is gradually decreasing. What we are concerned about is that what is the bound? What is the maximum that the spectrum, the magnitude can hit? What is the maximum value? And that will determine that whether there is any improvement is required, or we can go ahead with the existing design. Okay. So we need this bound, that is the spectral bound. Okay. And we specifically talk about the magnitude spectrum because that is the most important aspect. The phase spectrum is also important, but mainly we talk about the magnitude spectrum, right? And we will also talk about the effect of rise time and fall time on spectral bound, right? Now, we already know what is rise time and what is fall time. If we talk about any waveform, so there is some rise time, there is some fall time, finite rise time, there is some fall time. Okay. Although we also talked about the square wave pulse where we assume that the rise time and fall time they are zero. But actually in practical scenario there is no waveform. whose rise time or fall time can be exactly zero. There is obviously some rise time and some fall time. But this is an ideal case where we assume that the rise time and fall time is zero. And if we talk about the trapezoidal waveform, then obviously there is some finite rise time and there is some finite fall time, right? So we will see that if we increase the rise time or fall time, or we decrease the rise time and fall time, what is the effect on the spectral bound? Then we will talk about the effect of ringing. So ringing is a phenomena. We will talk about it later in more detail. What is ringing? And then we will also talk about the spectral bounds of different linear systems. Okay. So we talked about linear systems where we can apply superposition, where we can apply the rule of scaling. So yeah, so we will talk about the spectral bounds of linear systems. Okay. So I will discuss the problems, and in between I will also discuss the a bit of theory portion so that we can relate that whatever problems we are solving. So what does it physically mean? What is the significance, right? Yeah. So before that, if you can recall that in the last discussion we talked about the Fourier coefficient, right? And we found out that the Fourier coefficient uh, of a square wave is this, right? So there is this DC part 2a tau by t, where tau is the uh, duration or tau is the duty cycle, you can say. Then we have these functions. They are also called the sinc functions. So sinc pi tau f or pi tau by t. So f is the frequency. Time period will be 1 by f. And then we have also this function where this is pi tower f and pi tower by pi tower by f, right? So this is the rise time. This is the rise time. Okay. So this is basically for a trapezoidal waveform, not exactly for a square wave. This is for a trapezoidal waveform, right? So because for square wave we are assuming that rise time and fall time is zero. So yeah, you can see we can divide this into three parts. So this is the first part, that is the C0 part. Then we have this part, we have this part. Okay. So now if we want to draw it asymptotically, that means we will convert them into log scale and we will plot them, right? Then we can achieve the spectral bound. Okay. Yeah. Let's just take this part, okay, for now, just this part. So this is a constant. If you were if you are operating at a particular duty cycle of tau and your time period is also constant, A is the amplitude of your clock. Okay. A is the amplitude. A is the amplitude. Okay. So what we can say that, so this is a constant part. So if we convert it to logarithmic scale, so 20 log and then this quantity 2a tau 2a tau by t, right? 2a tau by t. So this is obviously will be a constant of some value, okay, but with zero slope. The slope is zero, right? So this is the first part. Then we have this part. And if you have followed the lecture, you will know that this is a sinc function. So sine pi tau by pi tau f by pi tau f, right? If we take any generalized expression, sine x by x, suppose sine x upon x, when x, the value of x is very low, so x is very low, in that case we can approximate it as, we can approximate it as, so this value will be close, very close to x, so x by x, that will be 1, okay, that will be 1. But when x is much larger, in that case it will be closer to 1, so that value will be 1 by x, right, 1 by x in other case when x value is large. Fine. So if you take this, then what will be the, what will be the asymptote? So there will be a break frequency. That frequency will be 1 by pi tau. Okay. So till this point, it will be constant. We, because this is asymptotic, we can assume this till this point it is constant. Then it will have a negative slope of minus 20 dB per decade. Okay. So this is minus 20 dB per decade slope it will have. And next we have another portion, this portion. So this portion is also a sinc function and we can approximate it just like this, right? So the first portion will be constant, obviously, because this is a constant. And then the second portion, we can approximate it as 1 by x. So there will be minus 20 dB per decade slope. But already we have this minus 20 dB per decade slope due to this portion. That's why the effective slope will be minus 20 and then again minus 20, so minus 40, right? The effective slope now becomes minus 40 dB per decade. So is this point clear how we are getting minus 40 dB per decade?
Yes, ma'am.
Okay. So minus 40 dB per decade. Okay. So that's how we can get the asymptote of this function of the Fourier coefficient. Okay. Now let's see the problem. Choose the correct option referring to the figure below. You can see this is already a familiar diagram because we just discussed that this is the first portion, then this is the second portion, and then this is the third portion where the slope is minus 40 dB per decade. What is the statement 1? To reduce the emissions of a product, the rise or fall times of the clock and or data pulses should be decreased. Statement 2 is pulses having small rise or fall times will have larger high frequency spectral contents than the pulses having larger rise or fall times. So the concept is that if your, if suppose one of the clock waveform is like this and the other one is like this, okay, like this, you can understand that the rise time over here is higher than the rise time over here. So when your rise time is very low, that means the waveform is rising at a faster rate, right? And in that case, there will obviously be more high frequency components, right? the high frequency components, because here the dV by dt is much higher. You can understand the dV by dt is much higher. Why? Because here the voltage is, obviously the amplitude we can assume same here and here. The amplitudes are same, but the time is lower than this one. So the dV by dt is higher for this case. So obviously the high frequency components will be higher in this case. And why exactly that comes, that we will also discuss. But this pulses having small rise or fall times will have large high frequency spectral contents than the pulses having larger rise or fall times. This statement is correct. And the first one, to reduce the emission of a product, the rise and fall times of the clock or data pulses should be decreased. That is not correct. Okay. To reduce the emission, we will have to increase the rise and fall times, not decrease it. Okay. So statement 1 is false and statement 2 is true. Okay. This is the correct one. Because whenever we try to reduce the emission, we will have to increase the rise and fall time. Okay. Okay. So here we may note that you can see here there is one frequency that is pointed here, 1 by pi tau, and here second frequency is 1 by pi tau r. Okay, these are the two break frequencies. Okay, breakpoint frequencies. This is one, this is the second one. Okay, and from where is this coming? Just follow this expression. So here what is the term here? Pi tau f. What is pi tau f? Pi tau f we can also write as excuse me. So pi tau by t. Okay, pi tau by t, that is one term. Another term is pi tau r by t. Okay, pi tau r by t. Okay, so from here we are getting, this is the first break frequency, this is the second one. Okay, that's why it is written 1 by pi tau and 1 by pi tau r. Okay, if you, so how will you get that? So this is some angle, right? Pi tau by t, this is some angle. So if we want to get the frequency, then what will we do? So suppose this is some omega t theta, so it will become 1 by pi tau. Okay. So here tau is much greater than tau r. Obviously, because your duty cycle will be much higher than the rise time. This is the rise time, this much, and your tau is, suppose from, even if you consider from half amplitude point, then your tau is this much. So this is much higher than the rise time or fall time. Therefore, 1 by pi tau comes before 1 by pi tau r. Okay. Now you can imagine that if your rise time is too low, if your rise time is suppose very low, then this quantity 1 by pi tau r, 1 by pi tau r, if your tau r is too low, if this is too low, then this quantity becomes high, very high. You understand, right? So this point, this break frequency will shift in the right, in this direction, and this minus 20 dB per decade slope will continue for a longer time, and then the minus 40 dB slope will come. So instead of this point, you will get the high. Here the frequency is also increasing. So till this point, the higher frequency components will only have a attenuation of -20 dB per decade. But it would have been better if we get more attenuation, because we don't want these high frequency components. But we are not getting a higher attenuation because our rise time is very low. Okay, that is the problem if we keep very low rise time or fall time. So do you understand what is the problem? Hello.
Yes, ma'am.
Okay. Okay, so that's why so there is a trade off. So if you just, if your rise time or fall time is too high, that is also problematic, because in that case you are losing the actual pulse duration. So that is also problematic, and too low of a value is also problematic. So there is a trade off, and we will have to
Ma'am, actually, I have
select.
a doubt.
Huh.
For the actually, I have drawn two diagrams, top one and bottom.
Hmm?
For the top one, the rise time and fall time are higher for that.
Yes, yes, yes.
So, for that, the higher frequency components are not there, na?
No, higher frequency components will be there, but what i what I tried to tell is that if your rise time is suppose here. So you just compare these two scenarios. First, it was here, suppose, okay. So in till this point, you were having -20 dB per decade slope. So the attenuation was lower. Then the slope became -40 dB per decade. So the attenuation became more rapid, right? Because here the slope is much steeper.
Yes.
But if your rise time is, if you reduce the rise time, suppose, then this portion, this frequency point will come at a much later stage, right? Because now this is low, so this quantity will become higher. So instead of this point, suppose it appears at this point. So till this point you will have -20 dB per decade slope, then the -40 dB point will come. So that's why till this point you are having a much lower attenuation, because here the slope is low, -20 dB, right? But at high frequency you want higher attenuation. The higher the slope, the better attenuation you get, right? Because you see here, for a particular point here you get this much attenuation, and for this point you get this much, so this is the attenuation from this point to this point. So the amplitude is getting higher if your attenuation slope is low. You understand, right? So
Yes, ma'am.
at the same point, so you are getting lower and lower attenuation because your slope is lower. So that's why we always want higher attenuation, higher. So -40 dB is preferable over -20 dB per decade slope, because we are getting higher attenuation at higher frequencies.
Okay, ma'am.
Okay. Okay. So let's see the next question. So question number 2 to 5, they are connected data questions. Consider a trapezoidal pulse train with peak amplitude of 1 volt at a frequency of 10 megahertz, having a duty cycle of 50%. The rise time of the pulse train is 4 nanosecond. At what frequency range is the level observed to be half that of the peak spectral component? So first of all, we get the peak spectral component till this point. This is the peak value. Then it gradually reduces, then at -20 dB per decade, and then at a higher rate it decays. Okay. This is the first frequency, suppose F1, and this is F2. Okay. These are the two break frequencies, and this is the peak amplitude. they are asking in which frequency range this we will get an amplitude which is half of this value. So suppose this at this point this is the half of peak amplitude. So at which frequency range? Okay. So suppose at something like this. Anyway, so what is the first task? The first task is to find out the frequency, these two frequencies, F1 and F2. Okay. So you know what will be F1? F1 is 1 by pi tau. This is the first frequency, right? Where the attenuation begins. So can you calculate and tell what are you getting? So your frequency is given 10 megahertz. You can find out what is your time period. Time period is 1 by f and duty cycle is given 50%. So your tau will be 50% of the time period. This is 10 multiplied by 10 power 6. This is our time period. Okay. This is our time period and what is tau? Tau is 50% of this value. So tau is 0.5 t. 0.5 t. Right. So this is 1 by pi into 0.5 and this portion will come in the numerator. So 10 power 7 over here. So did you get the value? So I already calculated it. So this comes out to be 6.36636 megahertz. This is the first point. Okay. Similarly, we will have to calculate what is F2. F2 is 1 by pi tau r. Sorry. 1 by pi tau r, where tau r is the rise time and the rise time is given 4 nanosecond. From here we can calculate. and it comes out 70 79.57 megahertz. 57 megahertz. Okay. 7 megahertz. So the frequency range is between 6 megahertz to 80 megahertz. Okay. So approximately this is close to 6 megahertz and this is close to 80 megahertz. But you can also verify. What you can do is you can exactly calculate what is the frequency at which you are getting the half uh, half of the peak amplitude, and by that after computing it you will be able to see that the frequency falls between this range 6 megahertz to 80 megahertz. Okay. Okay, so till this point is it clear?
Yes, ma'am.
Okay, so what is the value of the asymptote at 1 megahertz? So we just now found out that the frequency range is from 6 megahertz to 80 megahertz. So 1 megahertz is obviously below that point. 1 megahertz doesn't fall in that range. We will have to find out what is the value of the asymptote at 1 megahertz. So from start to 6 megahertz, the value is constant. And what is that value? That value is the magnitude we can find out, that is 2a tau by t. That is the magnitude. Okay. That is the magnitude. And then we will have to convert it to log scale. So 20 log 10, 20 log 10, then this quantity 2a tau by t, 2a tau by t. Tau by t is 0.5 because the duty cycle is 50%. So tau by t is 0.5, and then 2, the magnitude is 1 volt. The magnitude is 1 volt. It is given. So capital A, this is 1 volt and 2. So this is 1. Log 1 is what? Log 1 is 0. So this is 0, 0 dB volt. Okay. 0 dB volt. But here you will have to be very careful. Here the unit is not dB volt. Here the unit is dB microvolt. We will have to convert it to microvolt. So here we got that 20 log 1, right? 20 log 1 means 20 log 1 volt means 1 volt. If you convert it to microvolt, this is 10 power 6 microvolt, right? 1 volt means. So we are converting it to dB microvolt. That gives us what? That gives us 120. So 0 dB volt, if you want it to convert to dB microvolt, we will straight away add 120 with it. Okay. We will add 120. Is this fine?
Yes, ma'am.
Okay. Okay. So I have added this question. So find out the exact frequency at which the amplitude becomes half. Okay. We will have to find out that frequency at which we will get half of the peak amplitude. So This is our peak amplitude. We just found out, right? 120 dB microvolt. And these are the two frequency breakpoints. The values of those frequency points we have also computed. Suppose the magnitude at this point is M1 and the magnitude at this point is M2. Sorry, no, so at which point we can take that? At which point we are getting half of the peak magnitude, that we can assume M2, suppose, okay? And this is suppose M3. Then how we can write this? This is just a straight line, right? Straight line equation. So we can write that log M2. You mind that M2 is the point where we are getting the half magnitude. Okay, this is the so this frequency we need to find out. Suppose this is F. This frequency we need to find out, and this is half of the peak amplitude. Okay, suppose. So log M2 minus log M1, log M1, and this is in numerator. In denominator, what we have? We have log suppose this is log omega minus log omega 1 is equal to minus 20, because the slope is minus 20 dB per decade. So we can write the slope is minus 20. Okay. Now just simplify it. So this numerator becomes log 0.5, right? Because we are trying to find out the half magnitude frequency. So this is log 0.5, and here what we have? We have minus 20 log omega by omega 1. Omega by omega 1. And as we are taking the ratio, we can simply put the frequencies. They are omega and omega 1, they are angular frequencies, but we can also directly put the frequencies because we are taking the ratios, right? Omega 1 we already know, we can take 6 megahertz, okay, and this part is already known, so we can find out what will be omega or what will be f, this frequency point, right? So can you compute it and tell me the value of this frequency f? So let's see. Log 0.5, let's calculate. Log 0.5 is, this is minus 0.301. 301, and here this is minus 20 log suppose f by, you can take 6 megahertz or you can take the exact value that we computed, some 6.33 or something I think we got. That also you can use. Okay. Yeah. F is equal to, so from both sides we can cancel the minus sign. So this is 6 into 10 power 6 into 1.03035. So did you guys, any of you got this value? Is this understood? Just let me know if the calculation seems okay. Okay, so we will go to the next problem. Find out the two frequency breakpoints if the duty cycle is 20%. Till this point, we were calculating considering that the duty cycle is 50%. Now, if duty cycle is 20%, that means tau by t. If tau by t is equal to 0.2, in that case, what will be the frequency breakpoints? So this is very simple, right? We know what is capital T, what is our time period, because frequency was given 10 megahertz. So this was 10 power 7, right? This was our time period, second, in seconds. And we just have to multiply 0.2 to find out what is tau. Then the rest of the part is very easy. You just have to find out what is 1 by pi tau. What is 1 by pi tau and what is 1 by pi tau r. See here, this frequency will remain same because rise time remains same. So we don't have to compute this again. This was, I think, 80. This was 80 megahertz, right? This was 80 megahertz. Okay. And only this will change the first frequency breakpoint. So basically, this point will change, right? So now we have decreased the tau. That's why this frequency will increase. This frequency will increase. Okay, let's see. So 1 by pi 0.2, 0.2, and over here we have 10 power 7. Okay. So what is this value? Pi into so this is 1.591 into 10 power 7. 10 power 7. Just convert it to megahertz. So 110 will be multiplied. This is 15.91 megahertz. 91 megahertz. So almost 16 megahertz. So we can see that this frequency has increased. Earlier it was at 6 megahertz. Now it has become 15.91 megahertz. Okay. So we saw what is the effect when we reduce the duty cycle. The more you reduce the duty cycle, the more this first frequency point will increase. Okay. It will shift towards this side gradually. So till this point, is it fine?
Yes, madam.
Okay. The next question. In a system, radiated emission is observed. The best option to reduce the radiated emission is, what are the options? To reduce the amplitude of the clock, to reduce the fundamental frequency, to reduce, okay, so that two options are repeated. So these are the same options. So to increase the rise or fall time of the clock. So if you reduce the amplitude of the clock, that doesn't serve the purpose, right? Because in that way, your frequency components will still be there, right? If you reduce the amplitude from, suppose earlier it was here, but now it is here, but still you are also curtailing your actual waveform because you are reducing the amplitude. Okay. And reducing the fundamental frequency also doesn't serve the purpose. What you will have to do, you will have to increase the rise and fall time, as we already discussed towards the beginning, that if you increase the rise or fall time, in that case you can just shift this point, this minus 40 dB per decade from where it starts, you can shift this point towards towards this left, and then you will get more attenuation for the high frequency components. Okay. So the way to reduce the radiated emission is to increase the rise and fall time of the clock. The next question is, varying the duty cycle has no impact on the high frequency components of the trapezoidal pulse. And statement 2 is varying the duty cycle only shifts the first frequency breakpoint, hence it has no effect on the high frequency components of the pulse. So what do you think? Are the statements true?
First one is false.
So we are varying the duty cycle, right? So we are varying tau. We are varying tau, that means. So when we saw that when we are varying tau, in that case, the first in one question we saw that we reduced the duty cycle, and this first frequency breakpoint shifted towards the right side. It increased, right? From 6 megahertz, it increased to 15 megahertz. But does it affect the high frequency components? Like what high frequency components you were getting, does it affect it? So now the minus 20 dB per decade slope will start from this point. Okay, so this point basically shifts from here to here based on what is your duty cycle. But does the high frequency components change if we change the duty cycle?
No.
No, right? So the first statement is true and the second statement is also true. Okay, this is the statement 1 is true and second statement is the correct explanation of statement 1. Fine.
Okay, man.
Okay, okay. Okay, so I will take a 5-minute break and then we can start the rest of the problems. Okay?
Okay, madam.
Okay.
Hi, Somshekar. Where are you from?
Hey, hi. I'm working in Germany and I'm working for a company called Cummins.
Okay, actually, my
Oh,
friend, there is one friend whose name is also Somshekar. So I thought you might be my friend. So just casually asked.
no, 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 no. What about you guys?
Yeah, I am doing PhD in NIT Goa.
Okay. You're doing PhD in what's the field?
Yeah, in electric vehicles,
Mm-hmm.
electric vehicle design.
What is your PhD thesis or
Uh,
topic?
Topic is actually designing bidirectional converters.
Okay.
So that is in-depth topic. But overall, there are different aspects I'm working on. One is in on EMI EMC
Mm-hmm.
for power electronics, and
Mm-hmm.
like to apply this in EMI EMC in the converters and all, something like that.
Mm-hmm. So basically, you're working for the DC-DC converters, right? Bidirectional DC-DC converter.
Not specifically DC to DC. It can be AC to DC as well, connecting to grid.
Oh, okay, okay. And doing the charging, you mean, right? Charging of the
Yes,
vehicles, for example.
from battery to grid and grid to battery. I mean the vehicle, grid to vehicle, vehicle to grid.
Mm-hmm. Actually, this is my first session. I have missed most of the sessions. I don't know how does this session goes, huh?
Yeah, so you're not worried about the exam, right? So are you
No, no,
planning to
no.
write the exam?
No, no. But I don't think it's an online exam. You have to go there and write, right?
Yes, yes.
Yeah, no, no. I don't think I can take the exam.
Then I think no worries for you.
Yeah. So how many people are totally in the class in this particular EMC EMI class?
A lot of people are not attending the live classes. I am not sure. Maybe 20. I think approximately. I think so. I am not sure.
This is the live class, is it?
Yes, this is the live class.
Oh, okay, okay. And that is the recorded one, is it?
Yes, yes.
The earlier one.
Maximum 10 people have attended so far for the live class.
Mm-hmm.
So I think most probably 20 overall for this course. I think
Mm-hmm.
so. Are you also from Andhra?
No, I'm from Karnataka. I'm from Bangalore.
Okay, so let's resume the session. Yeah, so now we will talk about a bit about ringing. Okay, so if you most of you must have some experience of PCB designing. So you know that whenever you design a PCB, there are some parasitics, right? So there will be some parasitic capacitances, there will be some parasitic inductances. So parasitic capacitances are associated with your device. If you are, suppose, using a semiconductor device, so you know that for suppose a MOSFET, so there are some parasitic capacitances associated with the MOSFET, the input capacitance, the output capacitance like COSS, CISS, and the transfer capacitance. All these things, I think you guys are aware of those things. You also have parasitic capacitances between like 2 points which are at different potentials, and in between there will be some dielectric medium. And also parasitic inductances we will get due to the traces. There are the traces of the PCBs. Okay. So due to these parasitic inductances and capacitances, at a particular frequency they will have resonance, right? And that frequency will cause some oscillations in your actual waveform. Suppose it was supposed to be like this, a perfect square, but instead of that, what you will get? You will get some oscillation, and gradually it will die down because there are some dissipative component, there are some resistive component also in your circuit that will help to damp out this oscillation, but you will get this ringing. That is called ringing. Okay. Due to that, there are some overshoots and undershoots in your waveform. And in some amount, they are okay, but if they are too high, then it may cause damage to your circuit, and it may also cause emissions, radiated emission as well as conducted emissions. Okay. So you will have to control this ringing. So what is the primary cause of ringing? Obviously, the high rise time, fall time, then more than 50% duty cycle, high DC gain. No, these three options are not correct. The parasitic inductance and capacitance in the circuit, this is the correct option. Fine.
But I think for the previous one, there could also be possibility of di by dt, right? The first one, the high rise time and fall time.
Yeah,
Because if
obviously.
your
So yes, that is
di
correct.
by dt increases, your inductance also increases, right?
Yes, definitely. So if you have a very high rise time and if you have a or very steep rise time and fall time, in that case you will get dV by dt, very high dV by dt also you can get,
Yeah.
and di by dt also. So
Yeah.
these are basically responsible for your EMI, for your emissions, obviously. But the
Mm-hmm.
ringing happens whenever there is some exchange of energy between inductances and capacitances, right? So this kind of oscillation comes
Okay.
when there is a
When
coupling
you have
between,
the when you
some
have the
inductance
you
and
have the LC circuit, oscillator
right,
circuit kind of thing.
right. So the inductance will provide some energy to the capacitor will get charged, and
Mm.
eventually again the capacitor will discharge and it will,
Yeah. Yeah.
yeah. So there is an exchange of energy between an inductive element and an capacitive element, and that causes this oscillation. So if we are specifically talking about ringing, then
Mhm.
this is the main cause, right?
Okay. So I mean, high rise time could also be a factor, but primary cause is only the primary inductance and parasitic
Yeah.
inductance and
So
capacitance.
So basically, ringing is one of the factors which can affect your emission. So there are multiple factors. There may be very high rise time, very
Yes.
low rise time, which makes the waveform very steep. And
Mm-hmm.
then this at these portions, because of very high dV by dt or di by dt, these emissions occur. Okay. And ringing is one of the phenomena which contributes to these emissions. So there are multiple causes for radiative emission or like conductive emission, and ringing
Mm-hmm.
is one of the phenomena. Yes. So yeah. So this high rise, rise time, fall time, very low high rise time, very low fall time. The effect of this on this emission that we just talked about in the previous problems. So did you join like just now or like we were there?
Yes, ma'am. I have just joined now. So yeah.
Okay. So just to give a brief, yeah, just to give a brief, I would concept. So basically, we just discussed that. I will go to the first slide. See, so we are talking about spectral bounds in this in today's lecture, in today's session. So this
Yeah.
kind of asymptotic plot we get when we suppose we are talking about a trapezoidal waveform,
Mm-hmm.
which has a finite rise time, finite fall time, and a pulse duration like this. So
Mm-hmm.
if you asymptotically want to plot it, you will get something like this, because the Fourier coefficient is like this, where you have a DC term like this, then you have the sinc functions. So this is the first constant part which has 0 dB slope. This is due to this part. Then eventually we have one breakpoint frequency at this point, which comes due to this portion, right? This portion
Mm-hmm.
where we get minus 20 dB per decade slope. And after that, we have similar sinc function at a frequency 1 by pi tau r, where tau r is the rise time. And it also contributes minus 20 dB per decade, but we already had a slope of minus 20 dB, so they add up, and we get effectively minus 40 dB per decade slope from this point
Yeah.
onwards, right? So if the rise time is too low, then this second frequency becomes very high, right? This 1 by pi tower, because this is low, this quantity becomes high, and this frequency point shifts towards towards right, like
Yeah.
you will get here. So the attenuation that you will get is only minus 20 dB per decade, not minus 40 till this point. And
Mm-hmm.
more and
Minus
more,
20 is almost like you're losing half of
yeah.
the signal, right?
Yeah, so losing half of the signal, but in for high frequency components, that is like we want more and more attenuation, because those are undesired components. We don't want them.
Yeah.
So
Okay.
the
Okay.
more
Yeah. Yeah. Mm.
attenuation we get, the more is better. That is better. So
Yeah.
if the earlier we start to get minus 40 dB per decade attenuation, that is better for our like
Mm.
for reducing the noise, right?
Yeah. Yeah. No,
So yeah,
again, it depends on the application, no, ma'am. Like,
yeah.
yeah, it's like I don't know. You're talking with respect to some microwave signals, or in case of like high frequencies where you have kilohertz. So I think depending on the application, we
Yeah,
choose
yeah,
whether
obviously. So
which attenuation is required.
this is just a general discussion, but obviously based on the application, like for some particular application, you may require a particular frequency component, like
Yes.
you
Yeah.
want that. So based on that, you will have to set the frequency and set these break points, all these
Mm.
things.
I think one question I had, ma'am, like this is a very fundamental, which I have not exactly understood is this
Yes,
this dB. What exactly dB means? Is it? I know it's only like the. So when one says it's like minus 3 dB slope, and then says
yes,
minus 20 dB slope, physically,
yes.
what does that mean?
So physically, see the so dB, we talk about dB when we convert the parameters in log scale, right?
Exactly.
So
Yeah. So it's basically like
this is the unit.
P out by P in, for example.
Yes.
Let us take the power
So
output to power input in logarithmic 10 scale, and then you get this.
yes, right. So if we see, the point is, if we do all the computations, all the analysis in time domain, right? So
Yeah.
suppose
Yeah.
you have some function yt, that is some function, and
Yeah.
that you will get with, like, by computing this mathematical operation. This is ht, and there will be one convolution with, suppose some input, some clock signal suppose is there, like this, some trapezoidal waveform, that is xt, okay? And
Mm-hmm.
what is ht is your impulse response of the system.
Yeah.
And
Mm-hmm.
this computation is kind of complicated. So what we do is we take them into the frequency domain. Instead of sticking to the time domain, we can do all
Shift to
this
the frequency
analysis in the
domain. Yes.
frequency domain, because then we can straight away get multiplication instead of this convolution, right? And
Mm-hmm.
then to further simplify it, suppose now we get y omega is equal
Mm-hmm.
to capital H omega and multiplied by x omega. So that is much simpler than the time domain operation, because we don't have to do all those complex mathematical, like, computations, right? And to further simplify it, what we do is we convert them to log scale. So if you convert them to log scale, suppose we do log y omega, then log h omega, we can have them in additional form, right? So if we just convert to log scale, then log y becomes log h plus log x, right? So log h plus log x. So in those case, when you convert it to log scale, you get all these slopes, minus 20 dB per decade. So decade means, suppose decade means a difference of, like suppose you have 1 hertz and then there is 10 hertz. So this is a decade, right? In log scale, we talk about decades because this is a log scale. So instead of linear, this is not a linear scale, you understand, right? So there will
Yes,
be
yes,
first
ma'am.
1, then 10, then 100, like this. So this is the slope in log scale. Just like
Yes, ma'am.
just like a straight line, you can imagine it. We know that y is equal to mx plus c. That is the equation of a straight line. Just like that,
Mhm.
what is the slope in that? That is m. M is the slope. Just like that, here the slope is minus 20 dB per decade. Right. So
Yeah, so
if
that means,
suppose,
so yeah,
say,
so that means in physical world, when the signal is
so
say
it
at
will,
frequency, yeah,
yes, yes. So it signifies attenuation or some amplification. So suppose for a particular, for suppose in one, you have a, have the magnitude. Okay. So you have the magnitude, and if your slope is minus 20 dB per decade, then at 1 hertz, if your magnitude is m dB, then at 10 hertz your magnitude will be m minus 20 dB. So this is the attenuation you will get, right?
okay,
Or
okay, ma'am. Yeah, yeah,
if it is the amplification, then it will be plus 20 dB.
yeah,
Okay.
yeah, yeah. Mhm.
Yeah. This is just a form of representation to ease, to like make the calculations easier. That's it.
Yeah, I agree, I agree. Yeah, thank you.
Okay.
Ma'am, in what applications we will have plus 20 dB? Uh,
That I will have to see. I am not sure at this point. Like there may be some application. So you can talk about, maybe see,
No,
suppose,
I think, madam, can you just correct me, like, to that question? If you take a band pass filter, no,
yeah,
wherein,
yeah,
so the
right, yes.
positive, the
And
positive
also,
rise will have a
yes, yes, and
positive
also
one, and
high pass filter also. Yes, high pass
yeah,
filter
high pass
also.
filter,
So
exactly, the high pass
yes,
filter
yes.
also. Yeah,
Yes, yes.
for example,
In
right?
that case, we want to allow the high frequency components and we want to attenuate the low frequency components. So in that case, the asymptote will be something like this. Okay.
Positive. It will
And
be positive.
right,
Positive
right.
plus 20
And
degree. Yeah.
exactly. And for band pass, we will have something like this. So we will allow a band of frequencies. Right. Yeah. So okay. Okay, yeah. So till this point we did. Okay, which of the following is the primary effect of ringing on a pulse with respect to EMI or EMC? So, ringing affects the amplitude of the pulse. Ringing affects the fundamental frequency of the pulse. Ringing affects the high rise time of the pulse. Ringing affects the spectral magnitude of the pulse. Okay, so the correct option is ringing affects the spectral magnitude of the pulse. This is the most pronouncing effect of ringing. Okay. So we will take an example to see the effect of ringing. Okay, so see this question. The increase of the spectrum due to a 1 megahertz square wave having V naught is equal to 5 volt and two ringing waveforms having the same K and alpha and ringing frequencies FR1 and FR2 respectively. Okay. So there are two ringing frequencies. Okay, suppose you have this, and then over this you have a ringing like this. Okay. And then suppose this, and there is a ringing where some negative. Okay. This and the ringing frequencies are given 10 megahertz and 50 megahertz. Okay. So there are two different ringing frequencies. We will have to find out what is the magnitude, right? What is the change in magnitude due to this ringing happening? Okay. So I am not going into the derivations. The derivations are already done in the lecture. You can go and see it, right? So suppose we had some square wave, and over that we have ringing. Over that we have ringing. Then we will treat them separately. The first we will take the Cn for the square wave, and then we will take the Cn for the ringing alone. For ringing, this is definitely a sine wave, right? So that is definitely some sine wave. So some k e to the power minus alpha t, because this is a damped out ringing. This is not a ringing that is like, we are obviously talking about a ringing which eventually damps out. So gradually the amplitude will decrease, and it follows a envelope of a exponential curve. That's why this e to the power minus alpha t comes, where alpha is the damping coefficient. Okay. And then we have a sine. Okay. We have a sine of omega rt plus theta. Okay. Plus theta, where theta is the phase of the initial phase of the waveform. For now, we can assume this is 0. Okay. So we will take this one and this one, we will compute separately and then add them. Okay. So you can check the lecture notes. Okay. So the delta value is, where what is delta over here? Delta is the extra, the rise in the magnitude spectrum that we get due to this ringing. If the ringing wouldn't have been there, it will suppose go like this. But now we are getting a jump, and this jump is occurring due to this ringing. Okay. So if you are using spectral analyzer, there you will see a sudden jump at a particular frequency. So that frequency is the ringing frequency. There some resonance is happening due to the parasitics. That's why we are getting this jump in the spectrum. Okay. That is the significance. So what is this delta? This delta is k by v, then p omega r, then we have omega r square plus alpha plus p square. Okay. Alpha plus p square. What are these parameters? So omega r is obviously the angular frequency of ringing. So it will be 2 pi fr. 2 pi fr. Okay. And fr is provided. Fr is 10 megahertz in the first case and 50 megahertz in the second case. Fine. And what is P? P is in omega naught. Okay. What is n? N is the harmonic order and omega naught is the fundamental frequency. Okay. And alpha value is also given. Alpha value is also given 10 power 7. Okay. So all the data is given here. K is given 0.5. This V, this is the amplitude, that is 5 volt. So P is what? P will be for the first case. So 10 megahertz. P is, see, the actual frequency is 1 megahertz. The actual frequency of the square wave, the fundamental frequency is 1 megahertz, and this is the ringing frequency. So what is the harmonic order? 10, because this is 10 times the fundamental frequency. So 10 times, then 2 pi into 10 power 6. Okay. 2 pi 10 power 6. This will be P. Okay. So we know all the values, right? We can calculate what is delta. So let's calculate what is delta. Delta is, I calculate. What will be another 2 pi. Just a second. So this is 10 power 6 7 pi. So parallelly, you guys can also calculate, and we can just see whether the calculation is okay. P is this, omega R is again 2 pi into 10 power 7 power 7. Okay. So if we just compute this part, so in the numerator we will get 4 pi square, and this 10 power 7 and 10 power 7, 10 power 14, they will cancel from the numerator and denominator because we have these squares. So over here we will get 4 pi square, and this is 10 power 7 square, that will get cancelled, then plus alpha plus p whole square. So 10 power 7 er square, that will cancel 1 plus, and p we just calculated. So this is again 4 pi square, 1 by 4 pi, this is square. Okay. This is the value of delta. No, sorry. This is not, this is 2 pi. This is 2 pi. 1 plus 2 pi. 1 plus 2 pi square plus. So correct me if I am doing some calculation mistake. Okay, please correct me. 210. Okay, and this is again 4 pi square. Square into 4. Okay, divided by. So I am getting 0.187. Just check it, huh? There may be some, I don't know whether I have done it correctly or not. Just verify it by yourself. Gonna 10 megahertz. So 10 to the power 7. Two point 523. Two point 523. 523 over here, and then we have 4 pi square. 4 pi square. 39.47848.523. This is 426. Okay. So plus and after that we have also this k by v, right? So this is 0.5 K is 0.5 and V is 5. So this is 1 by 10. Okay, so divided by 10 plus 1 log. So I think I am doing some calculation mistake. Just a sec. Let's see. For the ringing, we will see. Megahertz, okay. Okay, anyway, the process is fine, but I don't know, maybe I'm doing some mistake. Okay, just you calculate and in the next class you tell me, okay, what is the answer? I am getting some value
Okay.
that is, you understood the process, right? How we will do it. So just calculate it for 10 megahertz and 50 megahertz and tell me the correct option. Otherwise, we can discuss it in the next class, okay?
Okay, madam.
Okay, okay. Okay, so let's proceed. Yeah, so how does the selection of damping constant impact the trade-off between signal integrity and EMI reduction in electronic circuit? What is the first option? Choosing high damping constant always leads to superior EMC without compromising signal integrity. Now, that is not true. Why? Because whenever you are choosing high damping constant, that means there will be some dissipative element in the circuit, okay? And if there is some dissipative element, that will also affect your actual signals, which are useful signals, okay? So they will also get affected. So you can't always maintain the signal integrity completely. Sorry, with choosing high damping constant, that will also affect your other signals, okay? So obviously your EMC performance will improve because you are introducing damping, but your signal integrity will get affected also. Opting for low damping constant improves signal integrity but may increase the risk of EMI. Then damping has no significant impact on the trade-off between signal integrity and EMI. And the last is the trade-off between signal integrity and EMI reduction is solely determined by the circuit's complexity. Damping is not a relevant factor. Okay. So basically option B is correct. So opting for low damping constant improves signal integrity but increases the risk of EMI. Okay. So low damping means the ringing signal will continue for very long time. Okay, so it will get damped very slowly. Okay, so if you have very high damping, then it will damp fast. So like this. Okay, so if your damping constant is low, then risk of EMI increases. Okay, fine. Then we have another question. The time constant of an RC circuit should be much greater than the pulse width tau to significantly reduce the high frequency spectral component of the output. And statement 2 is the capacitor gets sufficient time to charge up to its final value before the pulse switches off and the output appears as a sawtooth waveform. Okay, so what is it saying? Suppose you have an RC circuit. You have an RC circuit and in the input you have a pulsed waveform. Okay, you have a pulsed waveform like this. This is the input waveform and you are seeing your output here across the capacitor. Okay, this is your V out. Fine. This, suppose we name it xt and xt is like this. Xt is like this. Okay, square wave pulse, simple. This is time period t and this is tau. This duration is tau. Okay, this you are feeding to this RC network, RC circuit. Okay, suppose your RC constant, you know, right, what is RC constant? So the capacitor will get charged via this resistance. Okay, and the time constant is RC. This is the time constant rate. Now suppose this RC time is much. So what is the first statement? That the time constant of an RC circuit should be much greater than the pulse width tau. So suppose RC is much higher than tau. Okay, this is much higher than tau. What does it mean? It means that the time the capacitor takes to get fully charged, that time requirement is much higher than this duration. Okay, this tau duration. If that is the case, what will happen? In that case, the capacitor will get barely charged. It will just start to charge when the pulse is turned off. There is no pulse. So again, it will start discharging. Okay. So your waveform will look something like this because you are giving very small time to the capacitor for getting charged. So it will get, it will just touch, it will like the amount of charging will be very small before it will again has to discharge because you are withdrawing the pulse. The pulse has become zero. Okay. And what it is saying that if that is the case, then the high frequency spectral content of the output significantly reduce. Okay. So how do we connect it with the high frequency spectral content? So basically, if you see here just by intuition, even if we don't do any calculation, you can see that the slope here is much lower. Okay, so it is gradually increasing and then gradually decreasing. Okay, so anyway, from intuition only we can say that your high frequency spectral component will reduce because here the slope is very low. It is very smooth. Okay, compared to this very high sharp square wave where the rise time is 0 and the fall time is also almost 0. Okay, and if you take the opposite case where your RC constant is much lower than your tau, in that case what will happen? So we can draw it. This is your pulse and it will quickly get charged because your time constant is very low, so quickly it will get charged and reach to this value. Okay, and while discharging also it will discharge like this. You can see in the waveform is much than this one. where it was gradual. So here your high frequency components will be higher, right? Component, the content will be high. So the first statement is obviously true. One is true. The capacitor gets sufficient time to charge up to its final value before pulse switches off and the output appears as a sawtooth waveform rather than as a square wave. So this statement is incorrect. Why? Because if your RC time constant is much higher, then you get sawtooth waveform, that is correct, but it doesn't get sufficient time to charge to its final value. So get sufficient time to charge up to its final value, this portion is incorrect. Okay. So here, excuse me, statement 1 is true, but statement 2 is false. Okay. Option C is the correct option. So did you understand what I was trying to convey?
Yes, ma'am.
Okay. So I hope you are familiar with this time constant, all these concepts you have studied, right? You must have studied before. Okay, so I think this is the last question. Okay. So a 20 megahertz square wave is passed through a low pass filter. So this is an LR circuit. This is the L, this is the R. If the square wave has a duty cycle of 50%, the high frequency spectral content is significantly reduced. If, yeah, sorry, do you have a question?
No, ma'am.
Okay, so this is an LR circuit, and we are giving a pulsed waveform in the input, and the duty cycle is 50%. Then the high frequency spectral content is significantly reduced if. Now for LR circuit also the same concept we can apply. So here the time constant is L by R. Earlier it was for an RC circuit, it was RC, here it is L by R. So this is some time constant, suppose we can name it some tau LR, suppose. Okay. So this is L by R. This is the time constant. So here the inductor will be energized via this resistor, and if when you withdraw the pulse, then it will get discharged. This is the input. Suppose this is the pulsed waveform we are giving in the input, and when the high frequency content will be low, when we will get a sawtooth waveform, because in that case the change is gradual, it is not very sharp change, right? And when it will resemble a square wave, that time only our high frequency content will increase, right? When it will resemble a square wave. But for that your L by R, your time constant must be much lower than tau. Okay. This is for when your spectral component is high. And for this case, your spectral component will be low. So L by R should be much greater than, so this is tau by 2. Okay. L by R. Right. We are talking in terms of frequencies. Okay. That's why this 2 by 2 term comes. So what will be your R in that case? So R is less than 2L by tau, right? This is the relation. So 2 into the L value is 1 micro. So 10 power minus 6. And what is tau? Tau is 50% of the time period, and our frequency is 20 megahertz. So tau is 0.5 by 20 to 10 power 6. Okay, 10 power 6. So what it, I think it comes 45.05. So this is 80. R should be much less than 80 ohm. Is it fine? So why why the high frequency content is low when we are getting this kind of waveform? That is clear, right?
Yes, ma'am.
Okay. Okay, so I think this was the last question. Okay. Okay, so do you have any doubt about any question or any concept?
In this case, ma'am, what do you mean by high frequency spectral? So this is basically high pass filter, low pass filter, no, ma'am?
Yes, so like we discussed, right? When there is a very sharp change in a waveform, at that time the low frequency components will be prevalent, right? So in this case, like where your
Come again,
time
ma'am. I
constant
didn't
is,
understand the last part.
so whenever there is, so suppose there is a very sharp change in your waveform, okay, so that time
Yes.
we get high frequency components, and there is a chance for EMI, right? High emissions. But if
Yes. Yes.
the
That's yes.
yeah, if there is a gradual change, smooth change in your waveform, in that case there is a lower chance that you will get any emission, or there is very high frequency components are present, that chance is reduced, right? If there is a gradual change.
Yes.
Yeah, so
Yeah.
if we analyze this case where your time constant of the circuit, that is L by R, that is much lower than
Mm-hmm.
this duration tau. What is tau? Tau is the pulse duration till the, so this is a pulsed waveform that we are giving in the input over here. That is a pulsed waveform, and
Yes.
the total time period is suppose t, and the duration when your pulse is
Okay.
present, that is tau, right? So if this
Yeah.
time constant is much lower than your this duration, okay, in that case the pulse duration is enough to charge energize the inductance. So you will readily, so there will be very sharp change, and it will readily get charged up to this value. Okay, the inductor will get energized in very quickly, so there will be a sharp change because the time is enough for the inductor to get energized because of this low time constant, right? But
Yeah.
contrary to this case, if your time constant is much higher, in that case it is not getting enough time to get energized, the inductor is not getting enough time to get energized. So gradually it will start in getting energized, but by that time you are already withdrawing this pulse, so again it will discharge. Okay, it will discharge, and again at the next pulse it will again get charged like this, and then gets discharged. So you are getting an waveform which resembles a sawtooth waveform, and here the slope is much lower than this one, where there is very quick change in the uh, waveform. You understood, right?
Yeah. But what I didn't understand is okay. But ma'am, what I'm trying to understand is here
Hmm.
you have a constant frequency square wave that is 20 megahertz, right?
Yes,
So we are
yes,
not changing. So it is not changing, right?
yes,
So
yes.
in case you're talking about a like um, a dynamic power supply, wherein you change only during the rise up time, then I agree that will have high frequency signals as well, and even the mix of high frequency and the low frequency. But
No,
now what I didn't
actually,
understand is,
yeah, so this waveform will remain as it is, this square wave. I am talking about this output voltage, okay? So the response I am
yes,
talking about. So
yeah,
this waveform will always be a square wave pulse, but
correct.
you are seeing the output at the across this resistor. So this waveform will either be a sawtooth or a square wave, or resemble a square wave. So this VT.
Yeah,
So you know, right? The equation is like, so usually if you have a LR circuit and you give a DC over here, so the relation is an exponential charging equation.
yeah. For the current, it
So
will be exponential,
yeah,
and the
for the
voltage will
current,
decrease.
yes,
Yes,
and
yes, this I know.
the voltage will drop
Decrease.
across the
It will be
resistor,
one minus.
hmm,
Yes.
and in the steady state, this will act as a short circuit for a DC voltage over here, and the entire voltage
Yeah.
drop will be across the resistor. Okay, so
Yeah. So it will be like a current source. Yes.
yes. So in that, so if you're so this so we you know that we write like this e to the power minus t by tau, like this. The equation comes the in the exponential term, it comes like this, where tau is the time constant of the circuit.
Yes.
Okay, so
Exactly. Yeah.
that's what I was talking about here. So the time constant
Yeah.
of the circuit. The difference is that here it is not a stiff DC, it is a pulsed waveform. So it will continuously change its so once it will charge, then again it will discharge, then again it will charge, and this will repeat.
Yeah. Okay.
Okay. So yeah, is there any so is
Ma'am,
there
can you
any more
explain?
doubt?
Ma'am, can you
Huh.
explain why tau by 2, ma'am?
So basically, I think L by R, this is the time constant, and tau is the
That is
pulse
because
duration.
50%, no?
So
Duty
no,
cycle
because
of 50%.
no, tau is 50% of this T, the time period. Your total time
Yeah, that's
period
the duty
till this
cycle is
point,
50%. Yeah.
yeah, and this duration is 50% of this whole duration. I think so. See, your T is what? T is 1 by F, and uh, so tau is equal to T by 2, so 1 by 2F. Okay, and mm, okay, so just a second, I will let's see. I think I have, yeah. So see over here. So this is written for RC. So if you just convert it to the frequency, so this is 1 by 2 pi RC. Okay. RC is the time constant. And if you want to convert it to angular frequency, so this is 1 by 2 pi RC. So basically what we are trying to do over here is, this is some time constant which is L by R. Okay. This is L by R. And what is your first break? If you remember, it was 1 by pi tau, the first breakpoint frequency. So we are comparing it with this, the breakpoint frequency. Okay. So You remember we computed this, right? So 1 by pi tau. This was the first breakpoint frequency. And then this is a time domain quantity L by R. So if you just want to convert it to frequency, we will take the reciprocal, right? R by L. Obviously, because we know F is equal to 1 by T, right? That you know. Frequency is 1 by time period. And then if we want to convert it to angular frequency, it will be R by L. And then, so this will be 1 by yeah. Okay. So that way they are computing, I think. You understood, right? What?
Yes.
So this is
Yeah.
for RC circuit, and similarly we can go for RL circuit. Okay. I think they have given some example. Yeah. So just converting it to frequency, and then this 2 pi term, and here this pi term comes, and from this extra 2 term is coming. I think.
So L by R time constant should be greater than half of the pulse width, right, ma'am? That's what the equation is saying.
Right. Yes.
Okay, thank you.
Okay. Okay, then. So let's conclude today's session then. And yeah, this question, yeah. So just please, I will upload the slides, okay, and you please try to calculate the values, okay. And in the next question, we can discuss this one, the ringing question, okay. Just calculate it, refer to the lecture notes, and then we will discuss what is the answer. Fine. Okay, then I will stop the recording.